Before there was anything, there was something that is almost impossible to name. Not darkness, because darkness requires space to exist within. Not silence, because silence requires time to pass through. What existed before the universe, if existed is even the right word, was something far stranger and far quieter than either of those. It was a state without dimensions, without duration, without location. Scientists sometimes call it a quantum vacuum, though even that name carries misleading echoes of emptiness. A quantum vacuum is not truly empty. It is a kind of restless potential, a field of possibility in which the laws of physics flicker and tremble at the very edge of existence. In this way, the deepest nothingness we can describe is still, in some sense, alive with latent energy. There are several ideas about what may have preceded our universe. Some physicists suggest that time itself began with the universe, making the question of before meaningless, like asking what lies south of the South Pole. Others propose that our universe emerged from a larger, pre-existing structure, perhaps a vast multiverse of parallel realities or a cycling cosmos that contracts and expands again and again across immeasurable timescales. Still others find meaning in the mathematics of quantum gravity, which hints that at the smallest conceivable scales, the boundary between something and nothing becomes blurred beyond distinction. None of these ideas is yet proven. All of them are honest attempts by human minds to reach beyond the edge of what is knowable. And in that reaching, there is already something beautiful. What we know with much greater confidence is what happened next. Approximately 13.8 billion years ago, from a state of unimaginable density and temperature, a singularity, a point in which all the energy that would ever become everything was compressed into a space smaller than any atom, something changed. The universe did not explode outward into pre-existing space. It is more accurate and more wondrous to say that space itself began to expand. The fabric of reality stretched, and in stretching, became real. This moment is called the Big Bang, though the name is a little misleading. There was no bang. There was no sound. There was only the rapid unfolding of everything. In the first tiny fractions of a second, events unfolded at a pace that strains the imagination. Within the first trillionth of a trillionth of a trillionth of a second, the universe underwent a process called cosmic inflation. During this brief interval, space expanded at a rate far exceeding the speed of light, not because anything moved through space faster than light, but because space itself was growing. What had been a region smaller than a proton became, almost instantly, a volume roughly the size of a grapefruit. This expansion smoothed the universe into the remarkably uniform structure we observe today, while also imprinting upon it tiny quantum fluctuations, microscopic variations in density that would, billions of years later, become the seeds of galaxies. As inflation ended, the universe was filled with a seething, brilliant plasma of energy and the very first particles. This was not a quiet place. The temperature exceeded 100 billion degrees. Quarks, the tiny fundamental constituents of matter, swirled freely in this hot, dense broth, bound together in shifting combinations, unable yet to settle into the stable forms we know today. This state lasted only microseconds. As the universe continued to expand, it also continued to cool, and cooling changed everything. Within the first second, quarks began to bind together into protons and neutrons. For every billion antimatter particles that formed, there were 1,000,000,001 particles of ordinary matter. Antimatter and matter annihilated each other in vast waves of energy. And that tiny imbalance, 1 part in a billion, is the reason anything at all remains. Every atom in your body, every rock, every star, every galaxy is the descendant of that small excess. The universe chose matter almost by accident, and from that choice came everything. Over the next few minutes, a period cosmologists call Big Bang nucleosynthesis, protons and neutrons began to fuse. Helium nuclei formed. Traces of lithium appeared. The universe was, at this point, roughly 3/4 hydrogen and 1/4 helium by mass, with only the faintest whisper of heavier elements. This ratio, set in those first minutes, is one we can still measure today in the oldest stars, confirming our understanding of those ancient moments with quiet precision. For the next 380,000 years, the universe remained opaque. Photons, particles of light, could not travel freely because the plasma of charged particles scattered them endlessly, the way sunlight scatters in fog. Then, as the temperature dropped to around 3,000 degrees, something remarkable happened. Electrons slowed enough to be captured by atomic nuclei. The first true atoms formed. And in that moment, the fog lifted. Light streamed freely through space for the first time. The universe became transparent. That ancient light still exists. It has been traveling for over 13 billion years, stretched by the expansion of space into microwave radiation. We call it the cosmic microwave background, and it is, in a sense, the oldest photograph ever taken. A portrait of the universe in its early infancy, glowing with the memory of its first clear morning. After this, a long stillness settled in. There were no stars yet, no sources of light, only vast clouds of hydrogen and helium drifting slowly through the growing darkness. Cosmologists call this the cosmic dark ages, a span of perhaps 150 to 200 million years, during which the universe was patient, waiting. But the tiny fluctuations seeded during inflation were doing their quiet work. Gravity was pulling hydrogen ever so gently inward, gathering it into filaments and sheets and nodes. The universe was weaving itself into structure. Then, perhaps 200 to 300 million years after the Big Bang, the first stars ignited. Imagine it. After hundreds of millions of years of darkness, light returned. These first stars were enormous by today's standards, hundreds of times more massive than our sun, burning hot and fast, consuming their fuel in only a few million years. And when they died, they did not disappear quietly. They collapsed, then exploded as supernovae of extraordinary power, seeding the surrounding gas with new elements forged in their cores. Carbon, oxygen, nitrogen, silicon, iron, the raw material of planets and life, were scattered into space for the first time. The universe was making something more complex than it had been before. From the wreckage of those first generations of stars, new clouds of gas collapsed into new stars, richer in heavy elements, and around those stars, for the first time, rocky worlds could form. Galaxy by galaxy, the universe organized itself across hundreds of millions of years into the grand cosmic web we map today. A lattice of filaments stretching across billions of light years, with enormous clusters of galaxies at the nodes and vast, nearly empty voids between them. Within galaxies, supermassive black holes grew at the centers, consuming gas and occasional stars, sometimes blazing as quasars bright enough to outshine entire galaxies, shaping the evolution of the structures around them. Somewhere in one unremarkable arm of one spiral galaxy, about 4.6 billion years ago, a cloud of gas and dust began to collapse. Perhaps it was nudged by the shockwave of a nearby supernova. Perhaps it simply reached a threshold of its own accord. Whatever the cause, the cloud began to spin and flatten, drawing most of its mass into a central knot that grew hotter and denser until, at last, nuclear fusion ignited. A new star was born. We call it the Sun. Around it, the remaining disk of gas and dust underwent its own slow sorting. Dust grains collided and stuck together, growing into pebbles, then boulders, then bodies hundreds of kilometers across. Planetesimals, which in turn collided and merged into planets. The inner rocky worlds formed close to the Sun, where only dense minerals could withstand the heat. The outer gas giants formed farther out, where volatile ices could condense and gather vast envelopes of hydrogen and helium. One of the inner worlds, the third from the Sun, settled at a distance that allowed liquid water to persist on its surface. We call it Earth. For the first 500 million years, Earth was a violent place. Bombarded by asteroids, racked by volcanism, its surface barely solidified before being remade. Yet chemistry was already at work in the warm, shallow seas, in hydrothermal vents on the ocean floor, in tidal pools lit by a younger, somewhat cooler sun. Simple molecules found each other, combined, recombined, and at some point, exactly when and how remains one of science's deepest open questions, a molecule arose that could copy itself. Life had begun. What followed is a story of its own, spanning nearly 4 billion years of biological evolution. But from the cosmic perspective, it is continuous with everything that came before. The carbon in living cells was forged in dying stars. The iron in blood was scattered by ancient supernovae. The water in the oceans arrived partly on icy comets. Life is not separate from the story of the universe. It is the universe becoming aware of itself, folding back through chemistry and biology, until, improbably, it produces creatures who look up at the night sky and ask where it all came from. Today, the universe is approximately 13.8 billion years old, and it continues to change. The most striking feature of the present cosmos is its expansion, not just continuing, but accelerating. Galaxies are moving away from each other at ever-increasing speeds, driven by a mysterious force that fills all of space.